German armoured units reached the Channel coast. British planners registered catastrophic equipment losses. Conventional anti-tank guns existed only in limited numbers. Most serviceable guns were prioritised for mobile formations. The Home Guard received mainly rifles and improvised explosives. Commanders judged this allocation inadequate against tracked armour. The War Office formulated an urgent requirement. Home defence needed a simple, cheap anti-tank projector. The design had to use minimal strategic materials. Manufacture had to exploit light industry and workshops. Lieutenant Colonel Stuart Blacker presented a candidate solution. Blacker had experimented with spigot mortars during peacetime. His earlier arbalest design had been rejected previously. However, the invasion scare altered procurement tolerance thresholds, and a design once dismissed now received renewed consideration. The new proposal became the 29mm spigot mortar. Informally, the weapon acquired the name Blacker Bombard. It aimed to deliver heavy bombs from static positions. The concept displaced a conventional barrel with a spigot. Propellant moved with the bomb rather than remaining fixed. The Bombard's core element was the steel spigot. This rod projected upward from a robust central block. The bomb possessed a deep tail tube containing propellant. Firing involved lowering the bomb tail over the spigot. An internal firing pin ignited the cartridge within the tail. Gas pressure acted directly against the bomb's enclosed tube. The bomb accelerated off the spigot into free flight. No conventional chamber or full-length barrel existed externally. The nominal caliber referenced spigot diameter, not bomb body. This arrangement simplified forging but complicated ammunition design. The complete weapon weighed approximately 112 pounds. On its mobile cruciform mounting, it approached 360. With tools and ancillary equipment, the total exceeded 400. The system broke down into multiple man-portable components. 5 men could redistribute the loads for short movements. Nevertheless, it remained effectively semi-mobile rather than mobile. The mass encouraged planners toward primarily static deployments. Concrete pedestal installations formalized this static orientation nationwide. The Bombard's cruciform mounting used 4 substantial steel arms. Each arm terminated in a ground picket or pad, so these absorbed recoil forces and stabilized the firing platform. A central socket held the main body and spigot. Elevation adjustment used a geared arc and handwheel assembly. Traverse on the cruciform base permitted full circular coverage. On concrete pedestals, traverse was more limited by design. The mounting sat within shallow pits or earth revetments. Camouflage netting often concealed the characteristic silhouette. Ammunition lockers were dug into adjacent earth banks. Crew organization normally involved 3 to 5 personnel. One man acted as layer and firer. Another handled bombs and passed them forward. Additional crew maintained ammunition supply from nearby lockers. A commander supervised engagement selection and range estimation. Manual range finding relied on simple optical or visual methods. No advanced sighting equipment was issued as standard. The official sight combined range scale and basic foresight. It assumed properly prepared range cards for local sectors. Home Guard units rarely possessed elaborate fire control instruments. The principal anti-tank projectile weighed approximately 20 pounds. Its body diameter significantly exceeded the spigot diameter. The tail tube extended beneath, enclosing the propellant cartridge. Inside the body sat nearly 9 pounds high explosive. Training pamphlets described the explosive as gelatinous in consistency. The fuse occupied a recess within the bomb body. Designers selected a nose fuse optimized for target impact. The intention was blast damage against armor and running gear. Direct perforation of thick armor plate was not expected. Instead, blast and spall would disable tracks and externals. The anti-tank cartridge contained approximately 270 grains cordite. This produced a muzzle velocity around 245 feet per second. The trajectory was therefore high and visibly arcing. Ballistic tables defined a maximum range near 450 yards. However, effective fighting range was much shorter in practice. Doctrinal guidance recommended engagements between 75 and 100 yards. At these distances, time of flight remained manageable. Range estimation errors still caused significant vertical dispersion. Hit probability depended heavily on range card preparation. Uncorrected first rounds often overshot or undershot entirely. A lighter 14-pound bomb served an anti-personnel role. It carried a different explosive filling and nose fuse. This projectile achieved ranges approaching 780 yards. Fragmentation patterns defined a substantial danger area around bursts. Units exploited this for area denial near defensive obstacles. The same spigot and mounting fired at either projectile type. Charge weights were adjusted through cartridge composition only. Practice bombs duplicated ballistic behavior using inert fillings. Concrete practice rounds allowed repeated firing against soft ground. Paint schemes differentiated live, inert, and drill projectiles distinctly. Bomb manufacture employed cast steel or iron bodies. Tail tubes required precise internal machining for spigot fit. Tolerances had to maintain concentricity under repeated firing cycles. Warped tubes led to erratic ignition or misalignment. Fins at the rear stabilized the bomb in flight. These fins were stamped and welded under controlled jigs. Quality inspectors checked fin pitch and alignment visually. Irregular fins increased yaw and degraded range performance. Explosive filling operations occurred in specialized filling factories. Fuses were installed only after explosive pouring and curing. The spigot itself demanded high-grade steel selection. It carried repeated impact loads from bomb ignition. Surface finish had to avoid stress-raising imperfections. Heat treatment produced a balance between hardness and toughness. Overhardened spigots risked brittle cracking under heavy use. Underhardened spigots risked bending, altering alignment irreversibly. Inspection involved magnetic particle or dye-penetrant methods. Reject rates at early factories were non-trivial. So documentation emphasized spigot integrity as a primary safety factor. Replacement spigots were manufactured but required skilled fitting. The concrete pedestal solution simplified repeated deployment significantly. Royal engineers poured pedestals at roadblocks and choke points. A steel pin was cast centrally into each block. The Bombard body dropped over this pin for mounting. This removed the need for the heavy cruciform frame. Pedestals standardized height and traverse limits at fixed positions. Hundreds of such pedestals remain visible in Britain today. Their survival illustrates the scale of original deployment. Pedestal siting considered arcs, fields of fire and cover. Many covered road junctions, bridges, and potential tank approaches. Mobility remained restricted despite breakdown capability. So carrying parties moved components using slings and simple handles. Soft ground and hedged lanes slowed movement considerably. Night redeployment required rehearsed drill and clear route marking. In practice, many units treated positions as essentially permanent. Alternative emplacements were occasionally prepared as contingency measures. Moving between these required pre-positioned tools and spare pickets. Time estimates for shift movements appeared in local defense plans. Recorded timings rarely compared favorably with theoretical assumptions. The system behaved as fixed artillery disguised as infantry equipment. Rate of fire depended on crew proficiency and bomb availability. Training pamphlets quoted between 6 and 12 rounds per minute. Higher rates demanded efficient passing and immediate loading sequences. Her heat build-up mainly affected the firing mechanism and spigot. No conventional barrel existed to overheat or droop. However, repeated firing accelerated spigot wear and structural stress. Manuals advised limiting sustained fire unless tactically essential. Ammunition expenditure tables attempted to control local stockpiles. Home guard units often held finite natures for specific tasks. Replenishment depended on higher formation logistics and rail transport. Standard firing drill followed a fixed sequence every time. The crew uncovered the weapon and removed protective covers. The commander confirmed arcs and selected the intended aiming point. The layer set approximate elevation using range indications or cards. A safety check ensured no personnel stood forward of muzzle. The loader received a bomb from the ammunition handler, and he inspected fuse safety features and tail tube condition. The cartridge state was confirmed before any loading movement. The loader lowered the bomb carefully over the spigot. Hands gripped only designated handling points on bomb body. Once seated, the loader announced the weapon as loaded. The commander issued a clear firing order when appropriate. The firer operated the trigger mechanism in a controlled manner. Ignition drove the bomb along the spigot and outward. All crew remained behind prescribed safety arcs during discharge. Observers watched for bomb flight and subsequent impact signature. If no detonation followed, misfire procedures were initiated. Misfire drill required a fixed waiting interval before approach. The bomb tail and fuse were treated as potentially armed. Disposal involved specialist personnel where available within formation. Safety reports noted several recurring hazards under field conditions. Insensitive fuses sometimes traversed soft targets without detonation. Occasional functioning bombs projected fragments backward toward crews. This created a documented risk zone behind the weapon. Improvised sandbag walls sometimes mitigated this backward fragmentation effect. Spigot damage produced unpredictable trajectories and increased danger considerably. Unauthorized modifications to mountings further compromised safety margins. The War Office reiterated adherence to manual instructions repeatedly. Investigations into accidents often highlighted procedural non-compliance. Home Guard turnover levels complicated consistent procedural enforcement locally. Procurement history shows extensive bureaucratic friction during adoption. Technical departments questioned the weapon's ballistic adequacy early. Some artillery officers preferred conventional gun development instead. Blacker lobbied persistently, emphasizing material and manufacturing advantages. Senior leadership eventually escalated the question to ministerial level. Political interest, including prime ministerial involvement, accelerated approval. Formal acceptance followed despite ongoing technical reservations. Production orders covered approximately 22,000 weapons overall. Distribution plans assigned many directly to Home Guard units. Regular formations received smaller numbers for local defense roles. Factories adapted existing machine tools for Bombard component manufacture. The railway workshops and smaller engineering firms participated extensively. Patterns and jigs standardized cross-plant dimensional consistency. Central inspection teams audited adherence to design tolerances. Spigot and pivot assemblies underwent particularly rigorous examination routines. Welding qualifications were enforced for critical load-bearing parts. Explosive filling plants operated under separate Ordnance Department oversight. Transport of completed bombs followed standard explosive handling regulations. Storage depots segregated anti-tank and anti-personnel ammunition stocks. Color coding reduced misissue likelihood during rapid deployments. Training infrastructure grew alongside weapon distribution across commands. Home Guard schools demonstrated Bombard drill to course attendees. That instructors prepared standardized lesson plans and range practices. Students fired live ammunition under controlled supervision and recording. Recorded data fed back into pamphlet updates and guidance. Local units then replicated training with reduced live expenditure. Dry drill benefited from the weapon's simple mechanical interface. Cardboard, or wooden dummies substituted for live bombs during practice. Sight alignment and laying exercises required no explosive components. Classroom instruction covered fuse theory and propellant characteristics. Defensive planning integrated bombards into wider stopline systems. Many sat behind roadblocks covered by small arms fire. Others protected bridge demolitions or pre-prepared obstacle belts. Fire plans assigned each bombard-specific engagement sectors. An overlap with adjacent weapons attempted to avoid dead ground. Distance markers were driven discreetly into roadside verges. Range cards recorded bearings and elevations for reference points. Commanders briefed crews on expected axis of enemy approach. Fallback positions sometimes existed with second pedestals prepared. Transition between emplacements remained slow and manpower intensive. Combat expectations centered on engaging tanks at close range. The doctrine assumed tanks slowed by obstacles and fire. Bombard crews waited until armor entered pre-measured killing zones. First shot hit probability carried disproportionate tactical importance. Reloading under direct observation by tanks remained highly hazardous. If the first bomb missed, subsequent chances decreased sharply. Yes, the heavy projectile's blast still threatened nearby soft targets. However, armor unaffected could respond with machine gun or cannon. The weapon's success therefore depended on concealment and surprise. Static positions that fired prematurely exposed themselves unnecessarily. Reports on actual wartime combat usage remain limited. Few documented instances describe confirmed tank kills by bombards. This reflects both deployment context and rapid technological evolution. By the time invasion threat diminished, newer systems appeared. The Piat offered a more compact, infantry-portable alternative. Conventional 6-pounder guns improved availability within field formations. Consequently, bombards increasingly served as secondary defensive assets. Some installations persisted around airfields and coastal positions, and others remained as training aids or emergency contingency measures. Post-war, many concrete pedestals were simply abandoned in place. From an engineering perspective, the spigot concept had advantages. It concentrated strength where force transfer actually occurred. It allowed large-diameter bombs without corresponding barrel forgings. This reduced dependence on long, high-quality gun tubes. It simplified transport of ammunition within existing packaging frameworks. However, it constrained achievable muzzle velocities quite significantly. Higher velocities demanded longer spigots or stronger tail tubes. Longer spigots created handling and alignment complications in practice. Stronger tail tubes increased bomb mass and manufacturing cost. These trade-offs limited the system's anti-armor potential envelope. That the Bombard demonstrated sensitivity to manufacturing variations in bombs. Minor deviations in tail bore diameter-altered ignition characteristics. Loose fits reduced initial resistance and lowered peak pressures. Tight fits risked excessive friction and erratic release timing. Quality assurance procedures tried to bracket acceptable tolerance bands. Nonetheless, field units occasionally reported inconsistent range behavior. This complicated elevation setting for precise roadblock engagements. Commanders compensated by reducing engagement ranges further still. Close-range employment partially mitigated ballistic inconsistency issues. The consequence was even higher exposure for operating crews. Logistically, the weight of individual bombs required planning. 20-pound projectiles limited hand-carried loads by each soldier, and ammunition was normally pre-positioned in covered forward dumps. Replenishment from rear depots used trucks or local carts. Stacking arrangements in lockers maintained fuse safety clearance distances. Moisture protection relied on tarpaulins and simple wooden doors. Inventory returns tracked expended and remaining bombs meticulously. Ammunition natures were not interchangeable with other systems. This specialized supply chain added complexity to home guard logistics. However, strategic material usage remained comparatively moderate overall. Paperwork documented frequent debates over the weapon's continued utility. Some regional commands requested conversion to more modern systems. Others argued retention, citing absence of immediate replacements. Central authorities balanced these views against industrial capacity. And as Piat and 6-pounder production increased, Bombard priority decreased. New procurement favoured portable, crew-served or towed systems. The Bombard remained where removal offered little marginal benefit. In static lines, sunk cost justified continued limited use. Elsewhere, weapons were relegated to training or storage. Policy circulars recorded these phased adjustments in distribution patterns. Testing programs for the Bombard produced extensive technical data. Trials examined penetration effects against various armor plate thicknesses. They also evaluated blast impact on tracks and suspension. Results confirmed limited direct perforation, but significant external damage. Track breakage and road wheel destruction remained primary damage mechanisms. Turret and hull integrity generally survived near-miss detonations. An armor spall inside vehicles occurred occasionally with close hits. Trial reports framed the system as short-range harassment capability. They never equated it with true dedicated anti-tank artillery. This classification influenced subsequent doctrinal literature and training emphasis. The Blacker Bombard also served as conceptual predecessor technology. Experiences informed later spigot systems, including naval Hedgehog launchers. Knowledge of bomb design and tail tube interaction transferred. Approaches to fuse safety and misfire handling carried forward. Thus, the Bombard contributed indirectly to later anti-submarine developments. Its home guard role represented only one application vector. Within design history, it sits on a wider continuum. It links experimental interwar spigot ideas to operational systems. Engineering lessons outweighed its limited frontline combat record. Documentation ensured those lessons persisted beyond wartime emergency context. In summary, the Bombard met a constrained requirement. It provided an immediately producible anti-tank measure for home defense. It consumed fewer critical materials than full-gun systems. It harnessed dispersed industrial capacity through relatively simple components. However, effectiveness depended on very short engagement distances. Ballistic performance and fuse behavior limited reliable tank defeat. Static deployment and heavy mountings restricted tactical flexibility significantly. Crew survival prospects after firing were statistically unfavorable. As superior weapons entered service, its relative value declined. The Blacker Bombard remains a record of panic engineering.